Hello, I'm going to be showing off my progress for the custom feature for the milestone project, showing what I've done so far, what I plan to do, and what tools I used. The feature I chose to work on is creating custom shaders and or adding support for custom shaders and also adding in some features that help complement that developers using the engine could potentially use. One of the goals that I had when setting out with this was to make it completely backwards compatible with the old version of the engine so that all of the old test cases would work and that this custom feature would only be additional and optional features for the developer to use. Um, so to start, one of the first things I had to do was upgrade my version of SDL. Let's see, I'll have to open that in here. So I changed my version from SDL2 to SDL 3.4. Doing that for the most part was fairly simple. Integrating from one to the other is fairly seamless, and I really just had to rename a lot of function names. The only thing that did take a little bit of extra work was redoing the audio database. Um, in SDL3, different audio channels are managed as their own distinct objects, so that required changing some things around, but ultimately it still ended up being pretty simple to change once I read through some of the documentation. But just upgrading to SDL3, upgrading to SDL3 would have given me some amount of control over shaders on its own. It introduces something called a render state, so you can create a SDL renderer using a using an SDL renderer. See, I forget exactly which function you need, but if you can use a special function to create a SDL renderer that allows for more GPU control, and you do that through something called a render state. So when you're creating the render state, you can specify details such as what shader to use within the fragment shader stage, bindings to use, storage textures, storage buffers, and a couple other optional things. But this alone did not give me the level of control that I wanted. I would have liked to have control over the fragment shader because this could have... So one of the things that I think would be interesting to do would be to use compute shaders when computing the particle systems just to help optimize that. And without control over the vertex shader stage, that wouldn't be possible. One of the additional features I wanted to add that uses the custom shaders is I wanted to add support for custom meshes. So make it so that a developer can create a custom mesh within a Lua script and then use that mesh within rendering calls. And this, while it does give some control, still leaves SDL with full control over the vertex buffer and index buffer. And so it would not be possible to create custom geometry in that way. So instead, I had to adapt it over to the dedicated GPU API, which is a new feature in SDL3, um, so basically it's a lot more verbose, requires you to define a lot more things, and in making it work, I ended up having to create a lot of new files, a lot of new code, um, a lot of new classes. So for example, here's what my new image renderer class looks like. There's a lot going on here, but like here's where it actually goes through and performs the operations using a render pass. And so I have dedicated renders for the image, for the UI, for the text, and for the pixels. All of those look a little bit different from one another. But in the end, I ended up getting it to work. So as for some of the benefits that this gives, I have a quick example. So one of the things I made back in homework 7 was a test case that gives that displays a Mandelbrot set. And the way that it worked was it would compute all of the pixels on the CPU and then make individual draw pixel calls onto the GPU. And let's see, once this loads, I can show it. A couple other things I can show while I'm doing this is, so I mentioned the vertex buffer and index buffer earlier. So I have my own class here called a geometry buffer. And so here's all the code that I use to manage that myself. So I have a lot of, so here's like, oh, here we go. Okay. Yeah, so here's what it looks like. You can see even when it's just a small 256 by 256 window, it ends up being very slow. Right now it's running a little bit slower than, let's see, what would that be? I'm not sure. Okay, but as I zoom in, it becomes lower than 10 FPS. And this is only running with 40 iterations of the Mandelbrot set algorithm. And even then, it's still, it's chugging. But if I can, but with the new shader support, what I can do is rather than having the CPU compute each individual shader, I can have the CPU compute each individual pixel. I can have that computation done on the GPU. So now, even with a window size that I think is about 10 times more pixels, running with 2,000 iterations, it's now, completely smooth at, 60 FPS. And I'm sure it could go even faster if I were to remove the VSync from it. But just for the sake of not having to wait for it to compile again, I'm not going to do that. All right. And then I also mentioned that I wanted it to be completely backwards compatible. So I can demonstrate that. So here's the 7C3 test case. You have the UI rendering, you have the rotations, you have the text, right? So everything works completely as it did back in the old non-GPU version of the engine. And yeah, so any test case that worked in an old version will also work in the new version. As for what I still need, okay, I can also show off the, so here's what the current additional features are and what's available to the developers. So the main feature is the class of material. The material can be constructed by the name of the fragment shader and the name of the vertex shader. Those are shader files that can be found within a shader folder within the resources folder. One thing I did have to add to the engine is a default shader that can be used with the old versions of within older test cases. So all of the old draw options still exist. So you can do image.draw, image.drawex. Those work exactly the same, and they use a default shader. So you don't need to specify any materials for those. But if you do want to control the default shaders that are used, you can use get default material to get a reference to that default material. You can use set material to assign what the current material to be used is to something else, and you can also get a reference to that current material. And if you want to set it back, so if you wanted to set it back, you can either just get the default and then set the default, but I have a quick and simple function for that just called reset material. The material itself has its own set of functions that can be called on any material instance. It works very similarly to how Unity's API works, where you can set integers, set bools, you can set different vector amounts, and then set arrays of floats and vectors. Now, I also had to add a new vector3 and vector4 type. So at first what I did is I extended the original vector2 definition to include a lot more functions, and then I added all the same features for a vector3 and a vector4. Originally, I was just going to reuse uh, the Box 2D versions, but the version of Box 2D that I have only has a Vector 2 and a Vector 3. Supposedly, the newer versions have a Vector 4 included as well, but I felt it was easier just to define my own Vector 3 and Vector 4 class. Um, let's see, the other features that are there are the new drawing functions. So the first two are called Render Texture and Render Texture EX. These two are pretty much the equivalent to the Draw and Draw EX, with the only difference being that the material is specified as the first parameter. What this does is it effectively just says, instead of using whatever the currently set material is for this draw call, just use this material instead. And then the other new drawing function is Render Quad, which provides a material, an X, Y, width, and height. So instead of having a image that is used as the main texture for that draw, it and because without the texture you don't know what the size is, it specifies the width and height, but it assumes that the shader does not require a texture to use, or at least if it does require a texture, that those textures would be assigned on the material already. Another thing to add is that if a draw call requires a material, or if a shader attempts to use a material that has not been assigned, it will default to the same white texture that particles use as their own default texture. So that gets reused for this. Okay, now as for everything, as for the additional dependencies, one of the things I had to use is a library called Spear of Cross. Spear of Cross is, let's see, I have it open here. A tool designed for parsing and converting SpearV to other shader languages. Now, I'm using pre-compiled SpearV files. SpearV is the file format used for Vulkan, which is what my engine currently supports. So I'm not interested in converting the JSON to any other format. What I'm interested in is, let's see, where's the, yeah, reflection API. So this is the part of it that I'm interested in. So, for example, I use it here in order to retrieve all of the different uniform buffers and all the different textures that a shader requires, and I use that so that a developer doesn't need to define those values itself prior to creating the shader, and instead the engine just handles that for you. And I use the same thing here in defining the numbers of resources that each shader uses. Okay, so I think that pretty much covers what I've done so far relating to this. As for what I intend to do going forward, I still need to add support for custom meshes and creating an API for that. As I briefly mentioned, currently it only supports Vulkan as its main shader language, and the reason is because the engine still expects pre-compiled shaders, so shaders that are already in .spv format. SPV is not a writable format. Instead, I'm writing them in HLSL, but whenever I need to make a change to a shader, I have to manually recompile them. So what I would like to change is to have the HLSL be the main language that exists here, and use a tool called Shader Cross in order to compile from HLSL to the shader language that's required. So as I mentioned, for Vulkan, that's the SpearV files, and that adds support for any platforms that uses Vulkan. Out of the three that our engines use within this class, which is Windows, Linux, and Mac, Windows and Linux both generally have support for Vulkan, but Mac Mac OS does not. Instead, that uses let's see, I think it's MSL file, or it's like MTL or something like that. So I want to use that to convert from HLSL into the metal format that it uses, and so I will need to integrate this to make that work. That would also mean that it would use just-in-time compilation for shaders. Um, let's see. Another feature I want to add is okay, I also mentioned that I wanted to make the particle systems use compute shaders. So what that would mean is having a compute shader that updates and manages the data for each individual particle, and then the rendering of the particle system could be made to use GPU instancing instead of rendering each particle as an individual quad. This would greatly speed up the amount of time that needs to be spent on the CPU for adding individual particles. As it is, particles already work uh, and they work pretty well. So for example, in the 4.4 test case, I think this is running at about 50 FPS, which isn't bad. But if these were changed to use compute shaders and GPU instancing, it could be much, much faster. At least I would hope. Alternatively, I could also make it optional for what type of rendering it uses, but I think first I'm going to focus on creating meshes, and one thing I want to make is a sort of trail renderer similar to what Unity has using that mesh system. And once I do that, if I have the time, I'll shift gears onto creating the particle system compute shader. But yeah, so that pretty much covers everything that I have in store for the custom feature. So, yeah, thank you for listening.